All right, thank you very much, Amber, for that lovely introduction. So hope your capstone projects.
Actually, if you put it on both sides, I'll just put them together.
This talk was not designed. There we go. So welcome to the week 2 practical session. So hopefully by now you've watched the lecture that was already uploaded online. And again, as last week, I'll give you a quick recap as to what I was talking about. So this week, the topic was clustering. And we talked about, generally what clustering encompasses, how we need 2 key ingredients. And one is the proximity measure to measure similarity and dissimilarity between clusters, as well as actually defining what a cluster is, because I showed 2 examples here. And what do we mean by a bad cluster? What do we mean by a good cluster? We need to be able to define those as well. And generally, not just in deep learning, but machine learning in general, we need both of these in order to create a good clustering algorithm. Now, when we talk about deep clustering, we obviously need our neural network. So that's the deep learning component of these types of learning modalities. We also have our network loss and a clustering loss. And usually these will go together to create the final loss function. And that's exactly what we'll be doing today in today's practical session. So I talked specifically about one paper, and I tried to give you sufficient information to be able to implement it today. And the one I picked up was Vade, which stands for Variational Deep Embedding. And the reason I picked it is because you can use what you implemented last week in today's practical session. So I believe the TAs already have posted on Slack channels and gave you advice about actually training your models from last time and saving it. And you can do that in Colab, but also ask your TAs if you're not sure how to do that. And you can load it into today's Colab notebook as well. Alternatively, you can train that VE from scratch again, and I'll talk about that in just a minute. So just very quickly, Vade is a clustering algorithm which generates new samples as we did before with our mean and variance latent space and then sampling from that latent space. But it also has another kind of small addition to it in that it clusters data as well. And it's in a very similar manner in which that latent space works. And I will also get into that in a little bit. Now, I actually built this method after I gave the lecture. So there's a few things that I learned along the way when I was implementing this in Colab. So one thing I wanted to mention just generally about the entire architecture is that there's actually 3 phases to the learning phase in Vade. So I've kind of laid them out here. One is I called it the pre-training phase. So that's training your variation autoencoder so that the weights are all kind of set so that it does something intelligent. And from there, you kind of gather some Z encodings from your training set. And then that gets passed to what I call the pre-training phase, which is training up your Gaussian mixture model, which is the kind of the backbone behind the clustering part of Vade. So this is called pre-train. This function, the pre-training part, is called pre-train in the Colab template that you've already been provided. So you may opt to put the pre-training part inside the pre-train function as well, or you can load in your models and that will be the pre-training part done and dusted, and you don't need to worry about it. You just load it back in and use it. So those are your 2 options. I believe you've been recommended to load in your models, and I found that a lot easier when I was debugging, because you don't want to have to train every single time you make a mistake and you want to run your models again. So I found the loading part much more much easier to work with when you're debugging and building this loss function. So also what I want to say is that the pre-training part, which is about the Gaussian mixture model, the clustering parameters, the parameters for those have end with _C for cluster. And then for the Z encoding, I've labeled them _Z, I believe, for encoding. So I'll show you that in a second as well. So after you've done the whole pre-training component, then you can actually train your model, and that's very similar to how you would have done it in VE. So it's actually identical. I think I copy and pasted the code for the training component. So really, you just need to worry about the pre-train part and the loss function part today. Those are the 2 functions you'll be looking broken into. But please look at the whole thing, because it really makes sense when you look at the entire Vade architecture. And then obviously a test function. Again, that was copy and pasted from last week. There's no need to really edit it. So also, whilst I was going through Vade and I was implementing this, I noticed when I was going through this particular equation, and I'll just run through it very quickly again, you kind of have your cross entropy term at the top here, which is measuring how well your model is reconstructing your original input, which you're already aware of. Oh, sorry, these are the means, the encoding. So the difference between the encoding, so the latent space distribution and your actual data distribution. So you already did that with VE. The second part here is kind of looking at the intercluster relationship between your clusters and the actual cluster that has been selected during the training process. And then the last part here was kind of focused on the probability of the cluster that was selected as well. So I kind of briefly went over that. There was a question about going through it in more depth, which I might do in the second part when you've had a chance to really get going and you've got a chance to get to know all these variables. The reason I'm bringing this up again is because I didn't quite pick up initially that there's a mean and variance variable here, which you already have with your variational autoencoder, so that's the encoding space. And you have your mean and variance here, which is specifically for the cluster. So you actually have two sets of mean and variances, and I'll show you them in the code in a second as well. So just keep that in mind, which is why you have the underscore C for the cluster mean and variances parameters, and then I have underscore Z for the other ones, for this encoding one here. Yes?
Question. So this model is going through kind of a circular...
It still goes through that up and down fashion.
Yeah.
The authors just described it the other way around.
Yeah, so my question is basically, you said the pre-process or pre-step, right?
Yes.
So that mean and variance and the pi is actually part of the pre-step.
Yes.
So it starts from that point and then goes through the model.
Exactly. So the question is this a circular training mechanism? Because you have the Gaussian mixture model component at the start, and then you go through the training function. So the Gaussian mixture model, I realize, is just a way of initializing pi, mean, and variance. And then when you go through the training process, all that gets updated. So it's just a way of stabilizing those initial parameters. And then the training model will do all the rest. You don't need to touch it after that. So it's still a U in this framework. It's just you do an initial step before it.
I see.
Pass parameters in. Give it some prior knowledge. I guess that's the best way to explain it. Yes?
Could you please recap the big picture? What are the inputs, outputs, what are the objectives, the stages? I got a little bit confused.
It's a good question. So the question was, what are the inputs and outputs, and just give an overall structure of what's happening here. So your input is still an image, so it'll be the same as the batch that you were using last week, and whatever data you were using, whatever batches you were pushing through. And remember, last week we were discussing removing labels altogether, so there's no labels going through it. It's just the images.
So it's just unlabeled data.
It's just unlabeled data going through this network. And then it goes through here. It goes through your. It goes through here, and it outputs your reconstructed X as before. So that's what you got from your variational autoencoder, reconstructed X. You look a little confused, yes?
And mu and sigmas are the variational autoencoder distributions that are in the middle.
So that's this here. So you can get this. I can't believe it. I can't remember in my template if I retrieved all 5. So whether I retrieved the reconstructed input as well as the mean and variance for your latent space, as well as the mean and variance for your clusters, because really there's 5 parameters altogether that you're dealing with here. So you can look at this encoding space if you like, but the purpose of this network is really to do this part here, so the clustering part. So really, what cluster does this image correspond to?
So at what stage I have my VAE transformed into this Vade. So this is not. I cannot see variational autoencoder on this picture. What do I see here?
So if I took away this part here and connected this encoding to the input here, that should turn into a variation autoencoder because
yes.
input, output, yeah?
Yeah.
It's got the same number of layers here as it did in the encoder as well as the decoder. So this is your encoder, decoder,
Yep.
output, input, encoding latent space.
Yes.
Right?
What happens next?
What happens next? So one thing I should probably point out is that the clusters are learned at the same time as the latent space. So when it goes through the loss function and it back propagates, it's all going to be updated all at once. It's not necessarily one thing happens and then the next thing happens. It's all going to be encompassed into one. So when you build this loss function and you're incorporating the clusters themselves, it should learn something from the additional variables that you've added into this architecture. And therefore, when that update happens, everything should kind of learn relationships between your latent space, between the clusters. All of that is happening within the network, and it should update itself. So the output from here, what you want to get at the end of the day is a reconstructed X and the cluster it belongs to. That's what I kind of want you to be able to get from this network.
I still can't understand the computation graph here. So I have the encoder part.
Yes.
And then I have some clusters. What is that?
So you have your encoder, the latent space here.
Okay,
so
this is the latent
I think maybe I should switch to the code because I think the code will make it a little bit more visible how your computational graph looks,
okay.
Right? Because then you'll see inputs and outputs, and I think it'll be clearer. So let me just finish talking about this part here. So here in your equation, so first of all, I would recommend, and I actually mentioned this to a few people here, when I was implementing this, I had my Colab notebook up, the paper up with this equation. I can't believe what number, I can't remember what number this equation is, but it is in the paper. And I had the original implementation, which I gave you the link to, I had that up in a tab as well. Use all of them. Like if you can't figure out what's happening in one, look at another, and it just helps you just kind of get all the notes, the points together and clicks, and just helps it click and get it into your own Colab notebook. So when I was looking at this equation again after I'd implemented it, these red variables here are the ones from your latent space, from the encoder. So this lovely circular thing here. And then this blue cyan variables here are the clustering variables. So these are your variances for the latent space, the variance for the mean space, and then this is the mean for the cluster space, the variance for the cluster space. It'll all kind of come together when you start implementing it, I believe. And I will switch to the code so that we can show you some variables here. Okay, can everyone see this? Yeah, awesome.
Can you make it slightly bigger?
How do I make this bigger?
Yes.
Awesome. Right, okay. So this is, first of all, the VE, which you all saw from last week. So I'm just loading it in because I found that when I was loading in my models, it needed the VE to be in the scope of the Colab document. If the TAs know another way to do that, please ask them. This was the only way I could figure out how to do it, just to copy and paste it in. So I mounted the drive from my Google Drive so that I could load in my particular model. So this VE model object, I believe, so I used a 2-length encoding last week. And the clustering here, so the length of the encoding space has to be equal to the number of clusters. So because I created a 2-length encoding space last week, I have to create a 2-cluster model this week. However, if you're looking at, say, the MNIST data set, you really want 10 clusters, one for each digit. So if I was to go back, I would retrain this with a 10-length encoding. That's just a note, and I believe the TAs already provided a model that was 10-length encoded as well.
Yeah, we already have a model for 10 clusters, but you still need to modify the implementation here to let it know it has to look at
Yeah,
10
so
10
the
clusters.
comment was that the TAs have uploaded a 10-length encoded VE model, but adapt your code later on to adjust for that as well. So it's a good exercise when you're going through this. This is loading the data set as we did last week, so this should all look familiar. Okay, so this is Vade. So here, so I define the number of clusters here. So if you decide to go 10, all you need to do is change this when you're creating your Vade class. So I put it all into one class to make it a little bit cleaner and to differentiate between your VE and your Vade architecture. And I would recommend this. It kind of keeps everything together, and you can kind of separate out what's a VE and a Vade architecture as well. So we have the number of clusters here. We have some parameters here, which I've just initialized to none here. But then we're going to start with our pre-train function, which is going to set all these parameters. So pi, mu, c, and log c are our 3 parameters that are needed for this part here. So I'm going to go back here, for this part here. So our pi comes from the Gaussian mixture model, and so do the other mean and variances components as well.
Question, what is actually pi from this Gaussian mixture model?
So pi is, what is pi from our Gaussian mixture model? I can't remember.
What do you mean?
So we use our Gaussian mixture model to learn the weights in order to learn our mixture of Gaussians. So the weights from the Gaussian mixture model is your pi here. And so it should have.
So it's a vector.
It should be a vector of weights. Yes.
Okay.
Does it have
So
to
it's the
sum to
output
something?
of that
No,
Gaussian
it
So
doesn't
it's
use
an
sum to
output of
anything.
Gaussian mixture model. Okay.
So here, what you're going to do is load in your VE. So you'll notice here that I passed in my pre-trained VE model into the init function. You can do it wherever. I don't mind where you do it, as long as you get it into pre-train somehow. So I gave it in as a parameter here and set it here, gave it to the GPU, depending on the device, or CPU, depending on the device, and set my optimizer as well. So I did all of it here, but you can choose to load it in here as well. I really don't mind. So you'll need that to gather some Z encoding. So you'll use your training data, pass it through your VE, and just kind of collect lots of Z encodings, because that's what you're going to use to train your Gaussian mixture model. So that's your task. Load in your VE, train up a Gaussian mixture model using some Z encodings. And then you literally just set these parameters as it is here. So my Gaussian mixture model was called GMM. So that part is done for you. And really that's what I want you to focus on to begin with. And then we can really dive into the loss function and how we use these parameters later. But if you're getting ahead and you've already done this, or you've already started, or you're finding you're getting through this really fast, feel free to move on and go on to the loss function, which is where we take that equation and put it into code form. But we'll kind of talk about that later. I'll give you about 20 minutes to get set up, kind of look at this, get familiar with it, and so on and so forth. I will mention that this Vade class here has been repeated below because we incorporate our loss function there, but you don't need to worry about that just now. We'll talk about it in about 20 minutes. I'll just make sure I didn't miss anything in my slides. I think that's it. Yeah, we talked about the... Yeah, I think that's it for the first part. So if you can get your models loaded and get that pre-train function done, we can talk about the loss function in a little bit. Does that sound good? Fantastic. All right. I think we're good to go.